On October 19, 2017, everything changed. Robert Warwick was running through telescope images on Maui, doing what astronomers do every clear night, searching for moving points of light among the stars. The Pan-STARRS telescope had captured something, and at first it looked ordinary, just another space rock drifting through the cosmic neighborhood. Then the numbers came in. This object was moving at 196,000 miles per hour. That's 54 miles every single second. Fast enough to cross from New York to Los Angeles in just over a minute. That speed told astronomers something impossible. This visitor came from another star. Nothing in our solar system moves that fast. Our asteroids and comets cruise at a leisurely 12 miles per second on average. This newcomer was moving almost 5 times faster than anything bound to our sun. The speed meant it had been traveling through the vast emptiness between stars for millions, possibly hundreds of millions of years, before stumbling into our solar system. We gave it a Hawaiian name fitting for the first messenger from the stars. Oumuamua. The word means scout or messenger arriving first from afar. But speed was just the beginning. As telescopes worldwide tracked this visitor, they discovered something that made no sense. The object was tumbling end over end, and its brightness changed dramatically every 7.5 hours. This told us the shape was unlike anything we'd ever seen in space. Most asteroids are roughly round, like cosmic potatoes. Most comets are dirty snowballs with irregular but compact shapes. This visitor was different, really different. The brightness changes suggested something 10 times longer than it was wide. Picture a skyscraper lying on its side, spinning through space. No known asteroid or comet in our solar system has such an extreme shape. Yet compared to what astronomers would discover about its movement, the shape was just the warm-up act. The Pan-STARRS telescope sits on the summit of Haleakala like a cosmic lighthouse, sweeping the Hawaiian Seas for threats. Every night, this automated hunter captures images of space, looking for anything that moves against distant stars. But October 19th was different. When astronomers calculated the trajectory, they realized they were looking at something that shouldn't exist. This object wasn't orbiting our sun. It was passing through our solar system like a traveler on a highway, never to return. When you trace the path backward, it came from the direction of the star Vega in the constellation Lyra. But the object took so long to reach us, about 300,000 years, that Vega wasn't even in that position when the journey began. This visitor had been wandering through interstellar space since before modern humans walked the Earth. For decades, astronomers had predicted that interstellar objects should exist. The math said these wanderers should be out there. Finding one was like looking for a specific grain of sand on all the beaches of Earth. Once telescopes around the world started tracking this interstellar vagrant, the real mysteries began to emerge. This object had been battered by cosmic radiation for hundreds of millions of years. High-energy particles from exploding stars had slowly changed its surface color to a deep red, like rust on cosmic metal. The red color meant this traveler was old, really old. Yet even as astronomers celebrated finding the first confirmed interstellar visitor, the biggest mystery was still waiting to be discovered. The brightness measurements told an extraordinary story. As the object tumbled through space, its reflected light changed by more than 2.5 times as it rotated. That much variation meant only one thing: this was no ordinary round space rock. Most asteroids are roughly spherical, with bumps and craters. Even the most elongated asteroids in our solar system rarely stretch more than 3 times longer than they are wide, but this interstellar wanderer was different. The brightness changes suggested an object at least 10 times longer than its width. Some astronomers wondered if they were looking at a fragment. Perhaps this elongated shard was a piece of something much larger that had been shattered by a cosmic collision millions of years ago. But other scientists proposed an even stranger possibility. What if this object wasn't rock at all, but ice? Perhaps this visitor was made of hydrogen ice formed in the heart of a molecular cloud between stars. The extreme cold and pressure in these cosmic nurseries can create materials unlike anything found in planetary systems. Yet even this exotic explanation faced problems. The object appeared too small and too dark to be made entirely of ice. Its surface reflected light like rock or metal, not the bright, shiny surface expected from an ice body. Some researchers proposed the most radical explanation of all. What if this wasn't a natural object? Could this be debris from an alien civilization? While most scientists remained skeptical, they couldn't deny that this object challenged every assumption about natural space rocks. But the shape was only the beginning of the mystery. At 196,000 miles per hour, Oumuamua was traveling nearly 5 times faster than typical comets and asteroids in our solar system. The speed alone proved this object came from interstellar space. Nothing bound to our sun could achieve such velocity through natural gravitational interactions. Yet this visitor maintained incredible velocity, suggesting mysteries about its journey between the stars. The speed also meant observers had only a limited window to study this cosmic messenger. Unlike asteroids and comets that orbit our sun for months or years, this interstellar visitor was just passing through. It had already made its closest approach to the sun by the time astronomers discovered it. Telescopes around the world raced against time to gather as much data as possible before the object disappeared forever into the depths of space. Then, in June 2018, Marco Micheli and his team at the European Space Agency announced a discovery that would send shockwaves through the astronomical community. Oumuamua was not following the path that gravity predicted. As telescopes tracked its movement away from the sun, the object was deviating from the trajectory calculated using only gravitational forces. It was accelerating. The deviation was tiny, but measurable and consistent. In space, where there's no air resistance or friction, objects follow predictable paths determined by gravity alone. This visitor was apparently writing its own rules. The acceleration had the right characteristics to be caused by outgassing. When comets approach the sun, ice on their surface turns directly into gas, and this escaping gas acts like a natural rocket engine. But Oumuamua showed no signs of the outgassing that creates comet acceleration. There was no visible coma, the bright fuzzy cloud that surrounds active comets. There was no tail. Telescopes saw only a dark, apparently solid object tumbling through space. Yet somehow it was accelerating, as if it were a typical comet. This led to increasingly exotic explanations. Perhaps the object was ejecting material too dark to see. Maybe it was venting gas in narrow jets pointed away from Earth. Some scientists proposed that the acceleration came from the pressure of sunlight itself, acting on an extremely lightweight object. The light pressure theory required the visitor to have the density of foam or to be shaped like a solar sail. This explanation led to the most controversial theory of all. Avi Loeb at Harvard University, working with his postdoc S.H. Bialy, calculated that the acceleration pattern was consistent with an artificial light sail, a thin reflective membrane designed to catch sunlight for propulsion. The light sail hypothesis suggested that this visitor might be a piece of alien technology. Multiple research teams around the world began working to find an explanation for this cosmic anomaly. Alan Jackson and Stephen Desch at Arizona State University proposed that the visitor might be a fragment of nitrogen ice from a Pluto-like world in another star system. As nitrogen ice vaporized from the surface, it would provide thrust while being nearly invisible to telescopes. Then, in March 2023, Jennifer Bergner at UC Berkeley announced a breakthrough. Working with Darrell Seligman at Cornell University, Bergner had been studying what happens to ice when it travels through interstellar space for millions of years. The key insight came from understanding how cosmic radiation affects ordinary water ice during these incredibly long journeys. When cosmic rays hit water ice, they break apart water molecules. The energetic impacts split water into hydrogen and oxygen, but in the cold vacuum of space, these fragments can't escape immediately. The hydrogen becomes trapped within the remaining ice structure, like gas bubbles frozen inside a block of ice. Over millions of years, cosmic radiation could convert up to 30% of the water ice into trapped hydrogen gas. That trigger would be the warmth of approaching a star. As the interstellar wanderer entered our solar system and began heating up, the ice structure would start to change, releasing the stored hydrogen into space. The escaping hydrogen would act as a natural rocket engine, providing the acceleration that had puzzled astronomers. But hydrogen is essentially invisible to most astronomical instruments. This theory explained several key mysteries at once. It accounted for the acceleration without requiring visible outgassing. It provided a natural mechanism that could work on any water-rich object that had spent millions of years in interstellar space. However, the hydrogen theory still couldn't explain one crucial aspect of this cosmic mystery visitor: its extreme shape. The discovery of the first interstellar visitor revealed a sobering truth. We were essentially blind to small objects approaching Earth from the depths of space. The Chelyabinsk meteor of 2013 had already demonstrated this vulnerability. An object about 60 feet in diameter exploded over Russia with the force of 30 Hiroshima bombs, injuring over 1,000 people. Despite all our sky surveys, this cosmic projectile arrived completely undetected. Larry Deno and his team at the University of Hawaii realized that defending Earth required a fundamentally different approach. They needed to build a system that could scan the entire visible sky every single night, searching for anything that moved against the background of stars. Thus was born the Asteroid Terrestrial Impact Last Alert System, ATLAS. The name itself captures the mission perfectly. This would be our last alert system, the final warning before impact. NASA funded the project with $5 million in 2013. The first two telescopes were built in Hawaii, positioned on Haleakala and Mauna Loa observatories about 100 miles apart. By 2017, both Hawaiian telescopes were fully operational and scanning the northern sky every clear night. But the Hawaiian telescopes could only see the northern sky, leaving the southern hemisphere largely unmonitored. NASA funded 2 additional telescopes for the southern hemisphere, installations in South Africa and Chile that would soon make a discovery that would dwarf even the mystery of the first interstellar visitor. By early 2022, humanity achieved something unprecedented. 4 identical robotic telescopes separated by thousands of miles across the globe began working together as a single planetary defense system. Each telescope can image an area equivalent to 15 full moons side by side. Together, the 4 telescopes capture enough data every night to fill the memory of 50 high-end smartphones. The global positioning of these robotic sentinels creates overlapping coverage that ensures no blind spots remain. Each telescope follows the same precise routine every clear night, dividing the visible sky into 1,500 separate patches. Within hours of discovery, confirmed new objects are reported to the Minor Planet Center, the international clearinghouse for asteroid and comet discoveries. Since becoming operational, ATLAS has discovered over 700 near-Earth asteroids and 66 comets. The system has successfully detected 2 very small asteroids that actually impacted Earth, providing crucial validation of its ability to spot incoming threats. In July 2025, this global network would make a discovery that would reshape our understanding of visitors from other star systems. July 1, 2025 started like any other night at the ATLAS station perched high in the Chilean Andes. Computer algorithms processed each image within minutes, searching for the telltale motion that betrays asteroids and comets. At first, the discovery appeared routine. The detection software flagged a faint object moving slowly across the starfield. But as additional images accumulated throughout the night, something extraordinary began to emerge from the data. The object was not following the elliptical path typical of solar system objects. Instead, its trajectory showed the distinctive signature of a hyperbolic orbit, the same type of path followed by Oumuamua years earlier. The discovery triggered immediate alerts to astronomers around the world. Unlike the first interstellar visitor, this new object revealed its nature almost immediately. Through telescopes, astronomers could see a fuzzy, diffuse appearance surrounding a central bright core, the characteristic signature of a coma. This was not a dark, inert rock like Oumuamua. This was an active comet, complete with the glowing cloud of gas and dust that makes comets visible across the solar system. David Jewett and Jane Liu, veteran comet hunters, confirmed the activity. For the first time, astronomers were watching an active comet from another star system perform the same cosmic dance that our own comets have followed for billions of years. The official announcement came on July 2nd. The Minor Planet Center issued the designation C2025N1 with the official interstellar designation 3I, making it the 3rd confirmed interstellar object ever discovered. This timing advantage meant that observers would have months to study the object as its activity increased. Pre-discovery observations quickly emerged from telescope archives. The Vera Rubin Observatory had actually imaged the object starting June 21st. NASA's Transiting Exoplanet Survey satellite had captured the comet even earlier, with observations extending back to May 7th. These archived observations revealed that the interstellar comet had been active for much longer than anyone expected, suggesting that its activity was powered by more volatile materials than water, possibly carbon monoxide or carbon dioxide. The trajectory analysis confirmed what astronomers had suspected. When traced backward through time, the comet's path clearly originated from beyond our solar system, approaching from the direction of the constellation Sagittarius. Unlike Oumuamua, this new interstellar comet posed no puzzles about its acceleration. The growing coma and emerging tail explained its motion perfectly through well-understood physics. The first detailed images from the Hubble Space Telescope revealed a sight never captured before in human history, an active comet from another star system. The coma stretched over 8,000 miles across. Spectral analysis revealed the familiar signatures of water vapor, carbon monoxide, and carbon dioxide, the same materials that power comets born in our own solar system. But this cosmic visitor carried subtle differences that revealed its alien origin. The dust particles in its coma were larger on average than those typically found in solar system comets, telling a story of formation in a different stellar environment. The scale difference between the two interstellar visitors reveals just how much we missed with Oumuamua. While astronomers never determined the exact size of the first elongated visitor, estimates suggested it measured somewhere between 300 and 3,000 feet in length. This new interstellar comet dwarfs its predecessor by orders of magnitude. Early estimates suggest a nucleus several miles across, making it roughly 100 times more massive than the first visitor. When Atlas first detected this interstellar comet, it was traveling at 137,000 miles per hour relative to our solar system, 38 miles every single second. But as the comet falls deeper into our sun's gravitational well, it accelerates dramatically. By the time it reaches its closest approach in October, the comet will be racing at over 160,000 miles per hour. October 30th, 2025 will mark the most dramatic moment in this interstellar comet's billion-year journey. On that date, the cosmic wanderer will reach perihelion, its closest approach to our sun at a distance of 130 million miles, just inside the orbit of Mars. The approach to perihelion will transform this already active comet into a cosmic spectacular, as the sun's heat penetrates deeper into the nucleus, sublimating ice that has remained frozen since the comet's formation around another star billions of years ago. The increased activity will make the comet's tail grow dramatically longer and brighter. Models predict that the tail could extend for millions of miles, potentially making it visible to amateur astronomers with modest telescopes. However, the intense solar heating also creates observational challenges. As the comet approaches perihelion, it moves closer to the sun's position in Earth's sky, making it increasingly difficult to observe from the ground. Unlike the predictable comets that grace our skies every few years or decades, this interstellar visitor is making a once-and-forever appearance. Most comets in our solar system follow elliptical paths that bring them back to the inner solar system repeatedly. This interstellar comet follows a hyperbolic trajectory, a mathematical curve that approaches the sun once and then diverges into infinity. At 137,000 miles per hour, it carries far more kinetic energy than the sun's gravity can capture permanently. After perihelion passage, the comet will begin its eternal journey away from our solar system. It will first cross Mars's orbit in November, then Jupiter's orbit in early 2026. By 2028, it will pass beyond Saturn, entering the outer reaches where sunlight becomes too faint to drive significant cometary activity. The comet will continue outward for thousands of years, gradually fading as it moves farther from the sun's warming influence. Eventually, it will cross the heliopause, the boundary where the solar wind gives way to the interstellar medium. At that point, roughly 100 years from now, it will officially return to interstellar space. The Atlas telescopes perceive a universe invisible to human vision. Human eyes can see stars down to about 6th magnitude under perfect dark sky conditions. The Atlas cameras reach magnitude 20, detecting objects 100,000 times fainter than the dimmest stars visible to the naked eye. This extraordinary sensitivity comes from combining large digital sensors with precise optics and sophisticated computer processing. The 4 Atlas telescopes, separated by thousands of miles, operate as a single coordinated organism. When the Chilean telescope detects a moving object, computers at all 4 sites immediately receive the discovery data. Within minutes, the other telescopes can point toward the same region of sky to gather confirming observations. This global distribution creates overlapping fields of view that provide multiple perspectives on the same cosmic events. Every clear night, this coordinated network of robotic guardians scans the cosmos for objects that could threaten human civilization. Together, these surveys have catalogued over 90% of near-Earth asteroids larger than 1 kilometer across, essentially eliminating the risk of a surprise civilization-ending impact. The detection capabilities continue to improve each year as new telescopes join the global network and existing systems receive upgrades. The era of interstellar object discoveries has only just begun. Theoretical models predict that between 1 and 10,000 interstellar objects pass through our solar system at any given time. Most of these cosmic wanderers remain in the cold outer reaches beyond Neptune, too distant and faint for current telescopes to detect. But as our survey capabilities improve, we will begin finding these elusive visitors in unprecedented numbers. The Vera Rubin Observatory, beginning operations in Chile, will revolutionize interstellar object detection with its unprecedented combination of sensitivity and field of view. Computer models suggest that Rubin will discover between 1 and 3 interstellar objects every year, building a statistical sample that will transform our understanding of these cosmic messengers. The James Webb Space Telescope and upcoming extremely large telescopes will provide unprecedented spectroscopic capabilities for studying interstellar visitors in detail. These advanced instruments will detect trace organic compounds and exotic ices that reveal the chemical evolution occurring in other stellar environments. The discovery of visitors from other star systems has fundamentally altered humanity's understanding of our place in the galaxy. Before Oumuamua arrived in 2017, our knowledge of planetary systems beyond our own came entirely from indirect observations. Interstellar objects provide our first direct samples of materials from these alien worlds. The chemical analysis of interstellar visitors reveals that the basic processes of planetary formation operate similarly across different stellar environments. However, subtle differences in isotope ratios and trace element abundances hint at the enormous diversity that exists among planetary systems. The discovery of interstellar objects also reveals the dynamic nature of planetary systems throughout the galaxy. Every star system apparently ejects some fraction of its asteroids and comets into interstellar space through gravitational interactions with giant planets. This process means that material formed around one star can eventually be incorporated into other planetary systems, potentially spreading the chemical ingredients for life across vast galactic distances. The journey from the mysterious Oumuamua to today's sophisticated detection networks has revealed profound truths about our cosmic neighborhood. The enigmatic needle-shaped wanderer of 2017 taught us that the universe contains objects unlike anything in our experience. Its bizarre acceleration challenged our understanding of small body physics and demonstrated that even our most fundamental assumptions could be wrong. The Atlas network represents humanity's response to that wake-up call. The active comet discovered by Atlas in July 2025 provides a perfect counterpoint to Oumuamua, an object that behaves exactly as astronomers expect while carrying chemical signatures from another star system. Together, these discoveries demonstrate that interstellar objects come in varieties we're only beginning to understand. The technological advances driven by interstellar object research benefit all of astronomy and planetary defense. The same networks that hunt for cosmic visitors also protect Earth from asteroid impacts, discover supernovae in distant galaxies, and track satellites that threaten space missions. Perhaps most significantly, these cosmic messengers have changed how we think about our solar system's place in the galaxy. We now understand that vast amounts of material flow between star systems, creating an interconnected web of chemical exchange that spans the entire galaxy. Our Sun participates in this cosmic recycling program, both receiving visitors from other stars and contributing its own asteroids and comets to the interstellar population. We stand at the threshold of an era where visitors from other star systems will reveal the chemical and physical diversity of worlds we may never visit directly, bringing the cosmos to us, one cosmic wanderer at a time.